Welcome to the third part of the Project Skylark House Generator tutorial series. We will cover some interesting topics here, like matching attributes based on an ID and projecting attributes into tangent space. By the end, you'll have UVs that are always perfectly oriented towards the top. This will be interesting. In our simple example, if we have a look at our subnet, we just have one UV flatten node. It does look quite promising, and it is actually without much distortion because it's trying to unflatten the whole mesh, and because of the symmetry, it does quite a good job of preserving the direction of the roof. Although the issue that we have here is that the UVs are flipped on their side. We could try and undo this with a UV transform node, and I'll just show you what that would look like. We would have to rotate it by 90 degrees on this axis. It would mean that one side, in this case, will be oriented correctly, but the other side will be reversed. This would be an issue if the texture has any directionality or suggests the placement of roof tiles, so we will want to solve this a different way. It would be quite helpful if we had an attribute that we could use to independently UV these two sides of the roof. We can go up one level and go back inside the roof shape subnet and add an attribute wrangle to use our current primitive number as an ID. Type I at roof underscore ID equals I at primnum and set this to run over primitives. If we enable the visualization, we can see that it is correctly applied to the two sides. This is because we assigned this attribute before we did any extrusion, but on the extrusion itself, it did not correctly inherit or initialize that value. So we will have to make a couple of changes back in the subnet above, and we'll want to make some changes around the poly extrude node. So let's give ourselves some space. The main thing that's causing this issue is that poly extrude can correctly transfer the attributes if they exist on the point, but they will not be kept if they exist on the primitive. We can fix this with an attribute promote node. If we promote our primitive roof ID attribute to point, we'll see quite a good result. So the original name will be roof underscore ID. That will be, the original class will be primitive. And you can already see that this is kind of the result that we're looking for. We do, however, want this attribute to live on the primitive in the end. We can do this with an attribute promote at the end as well. We can just reverse this. The original class will be the point, and the target or the new class will be primitive. We do see an issue here at the top though. This is caused, if we have a look back at our poly extrude, by this prim having an equal number of points with a certain roof ID value as another. And if we have a look at the promotion method, it will take the average value and then round it up to an integer. One of them will be 0, the other one will be 1. Then the average is half, which rounds up to 1. So that's why we have this issue on the edge. We could try playing around with these, and setting it to minimum might solve it in this case, but it might not help in all cases. So let's just leave this as average because it works well for us here at the end. As you can see, no issue. It's just at the top. So essentially, we want this attribute promote to not modify any of the existing data, or any of the old data, I should say, because here everything was fine. The attribute was on the primitive, and then here at the end, the attribute is still in the primitive, but the values are messed up at the top. There are a couple of ways of doing this in Houdini. One of them would be with an attribute transfer node. But in this case, because really nothing much changed about the geometry, there's an easier way we can do this, and that's with ID matching. Let's start by creating an ID attribute, and I think it will become a little bit more clear. This will be set to primitives, and we'll type I at ID equals. This will be based on the primitive number, so type at primnum, close that off, and let's visualize this. That will be this one, ID. Each primitive will have a random color assigned, or at least that's how it is visualized, but it really is just a random integer. As we go down our graph, you can see that this value keeps getting preserved no matter what we do. We can use this fact to look up a value that one primitive has from any step previous in the chain as long as this ID value is consistent and present. If we have a look at this attribute promote, for example, if we ignore this strip at the bottom, we'll be able to look up the previous values. This will work even if all of the primitive numbers would change, because the ID would still be the same. One small correction that I will have to make is in the poly extrude. Instead of calling the front group roof edge detail, I'll be calling the side group roof edge detail. This will not make a difference for the rest of the network, but it will allow us to run this following attribute wrangle just on that group. So we can paste the name of that group right here with an exclamation mark in front to run this attribute wrangle just on these prims. Those are coincidentally also the primitives with the ID attribute that is valid. Call this top attribute wrangle ID so we know what it means, and then the bottom one, let's call this one reset roof ID. In this attribute wrangle, we'll be setting the ID attribute, so I at ID equals, and now the very specific syntax. This will be quite useful to know. I at, in this case because it's an integer attribute, otherwise it would be v at for vector or f at for float. Op input, so that's operator input 1, so that would be the second input on the node, underscore, then we have to specify the name. This would be roof underscore ID, and then close out with a semicolon. Just to be clear, to correct this small mistake, we're not actually setting the ID attribute, we're setting the roof underscore ID attribute. And by default, it will be using the ID attribute that we're visualizing right here to look up the previous value. So we'll need to connect the second input to the ID. And if we have a look at this result, change the visualization to roof ID. We will want to make sure that this attribute wrangle is also set to run over primitives and not points. And it has now been perfectly restored. Before and after the attribute wrangle, you can see this edge is now correct. Let's clean this up a little, and then we're done in the subnet. Let's have a look at how we can use this data inside of the roof UV subnet. We can add a for each named primitive loop, and we can run this over the roof ID attribute. So let's just plug this in, change the piece attribute, which is going to be named by default, change it to roof underscore ID, which is the attribute name that we've got for our project. And let's change the single pass just to see that it is in fact working. So one way we can do this quite simply is just by moving this UV fasten and putting it inside of our loop. You can see what we get. We get quite a good result, although the angle is slightly off. Let's think about how we want to solve this. We can still use this UV flatten as a base, but we would want to calculate how far off these UVs are from their target direction. With the polyframe node, we can analyze how an attribute changes over the mesh and use that to guide a vector. We can change the style to attribute gradient to, as the name suggests, create a gradient based on the attribute. This will be a vector in world space. First, we would need an attribute name to put in. This will be based on the Y position. We want a vector field from the bottom to the top of the mesh in the direction of the height. All we need to do is create the attribute in an attribute wrangle. It can be any name, but I'll call this v at y underscore vector, and this will simply be the y component of the position attribute. Let's type set v at p dot y, comma v at p dot y. The polyframe node only accepts vectors as input and not floats, which is why I'm converting this float into a vector like so. Just to show you what would happen, I can add the y underscore vector name right here in the attribute name field. Let's just, as a quick example, type f at y underscore vector equals just v at p dot y, and we can comment out the first line. We can see that the polyframe node will complain. Well, if we remove this line and just use the vector version, it does indeed find it. Let's rename this attribute and visualize it in the viewport. Let's call this up underscore tangent. And then if we press the I button, select this one, we can see that we now have a vector field guiding us in this direction. So what we could do next is for each point, see how far off the UVs are rotated in relation to this vector. So we've got this vector already, but we also need the UV space vectors. We can use another polyframe node for this and just copy and paste this. Change the attribute name to UV because we have already computed our UVs previously, and we need both the tangent and the bitangent. I'll just leave these at the default names, control middle mouse click to reset it. So that would be tangent U and tangent V. We can visualize these as well in a viewport just to give us an idea. That would be this one, and let me turn off the up tangent. So this one will be perfectly aligned with our UVs in the U direction, and this one will be in the V direction. And now we have all the input data to start computing the angle. This will be done in another attribute wrangle. But first, let's think about this a little bit from a theoretical perspective. Let's say in the simplest case, you've got two axes, x and y, like so, and you have one vector. Let's call this one A. It could have a length of 1, for example. This would be 1, 0. And we have another vector, and we take the dot product of A and B. B could be any angle. What this will essentially do is calculate or project this vector onto, in this case, the x-axis or the axis of A. The resulting dot product could be something like 1.2, for example. If you move this around, if you move B here, it could be something like negative 1.2. So this may be a slightly different way of thinking about a dot product, where usually you might just think you have one vector and you see how aligned one vector is. The closer it is aligned, the closer the value will be to 1. At a perpendicular angle, the resulting dot product will be 0, and at a negative one it will be -1. But if you leave these two vectors unnormalized, essentially you are just doing a projection. And we can use this exact idea for projecting into any space. So if we take the same axes, just imagine that our UVs are rotated like this. Our up vector might be pointed in this direction, and we can get the x and y components of this vector in UV space if we just project this onto this vector to get the x value and project it onto the y vector like so to get the y value. And we can just do this with the same trick, just using a dot product. So this will be fairly straightforward in Vex. Let's just define a couple of variables. The first one will be a vector. Let's call this up tangent, and we'll be reading this directly from the up tangent attribute. We will also want to make sure that we run this attribute wrangle over vertices. Then let's define our target space. I'm going to call this vector target space U, which will be V at tangent U. Change the U for V on both occasions. And let's convert our up vector into the space of the UVs. This will be done separately for x and y. So let's call this float converted x dot product of the target space U and the up tangent. Copy and paste this once again and just change the U for V again and call this one converted y. Then the resulting vector, we'll just expand this window a little bit. This resulting vector will be called up in UV space. We'll be creating a vector, again using the set function, converted underscore x and converted underscore y. What we will then want to do is calculate the angle between this up in UV space and let's say 0, 1. You might have learned this formula in high school. It would be something like cosine of the angle alpha or theta, whichever letter you want to use, equals the dot product of A and B divided by the lengths of A and B. We can make it easier for ourselves in Vex by normalizing our vector, so we don't need to divide by these two values, because if the length is 1, we're just dividing by 1. We'll be doing A cos of the dot product of our normalized up in UV space vector. Just copy this name, normalize this vector. The other vector that we're going to be using in the dot product will be our target up in UV space, you could say. This one would be 0, 1. This just means we want our target vector in UV space to be aligned with 0, 1. It does actually want us to use a vector 3 instead of a vector 2 for this dot product, which is not a problem. We can just change this to 0, 1, 0, and then add a z component to this one, so it can just be 0. This function will return its value in radians, which is not a problem, but just for intuition, we'll convert this back to degrees. We can do this by multiplying the value by 180 and dividing by pi. If you type pi like this in capitals, this will be automatically replaced with 3.14, etc., the whole value of pi, which is quite useful. We will want to assign this value to an attribute. Let's call this one angle equals, and let's have a look at this attribute value in our geometry spreadsheet. Type in angle, this will be on the vertex, and you can see we've got angle values hovering around 4 or 5, but it's not a singular value, and really we would want to calculate the average angle that it's off by, and then do just one UV transform at the end to offset it. Let's add another attribute angle, call this first one angle with target up. This top one we'll call y vector. Then the bottom one, let's call this one average angle. Align this all, put this off to the side. We will only need to calculate the average angle once, so we can run this over detail. We will now need to get all of the values of those vertices and get the average. You could use a function like unique vals to get all the unique values, but the problem is if you have 5 of the same value and 1 unique one, then the average won't be computed correctly because you're not taking the values into account that are the same, which would influence the average. All the vertices can be stored into an array. Let's call this one int vertices. It will be an array by adding the square brackets at the end. And we'll be using the expand vertex group function. And the group that we will be providing is just going to be an empty group. So this will just give us all of the vertices essentially. Then we'll want to run over all of those vertices. So let's say for each, then int vertex out of all vertices. Unfortunately, calculating the average angle is not very intuitive. For example, if this is our up vector and we calculate the average angle between this vector, which could have an angle value of 10, and this vector, which could have a value of, let's say, 350, if you add these two together, you would get 360, and you could divide by 2 to get the average, but that would mean that the average angle would be 180, which would be in the opposite direction, which is not what we expect. Instead, we'll want to average all of the x and y components separately, and then turn them back into a singular angle. So before our for each loop, let's create 2 float variables, float x, which we will initialize to 0, and float y, same, initialize to 0. Right. So let's start by reading the value of the angle attribute as is. We can do this inside of the loop. Float angle equals, we'll be reading this from the vertex that we're looping over. Vertex, from our current geometry, we'll be reading the angle attribute, and then using the index from the loop, which is called vertex in this case, we'll just have to add something to x and add something to y. We can convert an angle back into a 2D vector using cosine and sine. We will also need to convert our degrees back into radians because the cosine function expects radians of the angle. Close that off. Then we can copy this whole thing and just change the cosine into a sine. Then we can write this out back into an angle attribute. Let's call this attribute angle once again, but this one will live on the detail level. We'll use the atan2 function with the y and x components. We'll also want to convert this from radians into degrees with the degrees function. And semicolon at the end to wrap that up. Now if we check our detail level, we see that we have an average angle. We can now use this in a UV transform node to rotate our UVs. We'll want to change the Z component of the rotation, and we'll use that detail attribute that we just created, detail of the current geometry. The attribute is going to be called angle, and then the first component of the attribute, as we're dealing with a float, we'll just use 0. This is only relevant if you wanted to read the X, Y, or Z components from a vector attribute. And we can click on the rotate field on the left and see that our value is correctly being used. There's just one thing that I have overlooked, and this is very straightforward to add. If we have a look at another example, let's say that this is our UV space, and this is our target of vector. We want to know whether an angle is on the right side or on the left side. Both of them currently would be treated as having a value of 10, and if we had both of these values and we wanted to compute the average angle would still be 10, which in this case is not correct. These two should cancel each other out. We can multiply our angle by a sine. This will be a new integer attribute that we're creating right above, and we're going to be using the sine function as well, which will return either -1 or 1 based on whether it's a positive or a negative value. We can multiply our angle by a sine. This will be an integer attribute, which will be either -1 or +1, whether it's on the left or on the right side of our up vector. Equals, we'll be using the sine function as well, so this will get us the behavior of either returning -1 or +1, and we'll be plugging in our up in UV space dot x. So if this x value is something like -3, -0.5, it doesn't matter. Just any negative value, it will return -1 to be multiplied with our angle. Close that off, make sure that you add the multiplication symbol here after the sign. This will complain about an implicit cast from float to int, so just add the int function right before. And you can see with this fix, we've got our UVs perfectly oriented. Without this, if I just set this to 1, comment out the rest, you can see that it did not orient it correctly. To wrap up the UVs, we can use the labs textile density node. Just add it right after our UV transform. Set this one to scale UVs to match textile density. We should also make sure to switch off the UV layout inside of the textile density node. This does also provide us with a different option of correcting the UV rotation, but I find that my manual approach is actually a little bit better than the UV layout. Because we looped over all the individual pieces, we will also need to make sure that we add a fuse node at the end to get it back together. In the next part, we'll start working on a roof extrusion.